So think of any questions you might have, and I'll just stay around for the last half hour and answer anything, or try to answer anything that you throw at me. Before we begin, does somebody have any general question they want to ask that might be of general interest? We'll stop at 1 hour, if I can remember to set my alarm, and then we'll take questions at that point as well. So let me start in a minute. Okay, many of you who are going to go into combustion science, and along with maybe other things, you'll want to know about what's new and what's different and what might you be doing in the future. And so the last two lectures I'm going to give on turbulent combustion are going to address new topics that are very much of interest. I guess the conclusion we can draw from the last three lectures is we don't know enough to really move into new topics. Many of the undergraduates who take our combustion classes are surprised that we can't answer all the questions. You know, if you're not, when you were an undergrad, you know, you expected everything that was covered to be known material. But then when you took a turbulence class, you probably said, wait, there's a lot of things that we're talking about that we don't know the answer to. That might have been a surprise to you, maybe a little disappointing. And when we get to turbulent combustion, there's a lot we don't know. But partially premixed flames is a very important subject. We've had workshops here in this country, and the Europeans are having many workshops on partially premixed combustion, mostly because the industry people say, we want models that can simulate realistic situations. I've been mentioning General Electric and gas turbine engines, but also various internal combustion engines in which the combustion is not a premix and it's not non-premixed. It's a little combination of both. And we don't yet have good models, but we're starting to develop them, and maybe you'll get some ideas as you listen to this. So yesterday I told you about the non-premixed work, some simple models, and the work done by Rob Barlow and others at Sandia to get, and Driscoll in Darmstadt to get a database. Premixed flames, we have several, 4 or 5 models that are being used. And partially premixed flames is relatively new, and I'll give you some papers to look at if you're interested. So first I'll define partially premixed combustion. Now, even this is not fully agreed upon by the community, but I think we're starting to agree on this, that partially premixed means that sometimes there are premixed flamelets and sometimes there are non-premixed flamelets. Now, the only thing we've considered in our thinking is flamelets. So if there's a distributed reaction zone, then we are in another situation that requires even more complex models. But let's just limit ourselves to flamelet type models, flamelet type measurements, but both premixed and non-premixed are present. And Takeno from Japan had a group of students working with him doing DNS, and they analyzed a lifted jet flame, and they found that at the base of the lifted flame there were regions of premixed flamelets and regions of non-premixed flamelets. And so they started using this flame index, which we're starting to call the Takeno flame index. And it's a quantity that varies from 0 if all the flamelets are non-premixed to unity if all the flamelets are premixed. And this will help us to model these problems. So I want to talk about motivation, some models, some measurements that I've got measurements that we've done, and there are people in other labs who are doing measurements. and we'll talk about how this might apply to some problems. So here is the DNS of Takeno and Mizubuchi in Japan. They had a very large computer. They only dealt with hydrogen, air, and today we can probably do a little better, maybe methane air, but a simulation like this would be hard to do with complex hydrocarbons even today. But they have a lifted jet flame. There's fuel coming out of a tube and air being entrained in. And the red is the rich premixed region. The blue is the lean premixed. Green is non-premixed. And you'd say, where's the triple flame? Well, I don't know. I think you could argue there are some triple flames in there because the triple flame would be non-premixed would be green, and then it'd have some red and blue on either side of it. But the other question is, where's the flame base? Now you can see it's three-dimensional and unsteady, and so if I told you that in a concept in the past that the base of the flame, let's say this is the base right here, right at this point it has a propagation speed where it's trying to move upstream, and that would be the blue lean premixed right here. And this blue region would try to move upstream at some burning velocity, and the gas right at that point would be coming at it at some velocity, and if the two were matched, then at least at that instant, this region would stay there. But then at a later instant, the gas velocity would be higher, and it would push this blue region up, and maybe the gas velocity would be lower over here, and it would allow this blue region to come down. So you can see that it's clearly three-dimensional, and even with a laser light sheet, you're not going to solve the problem. You need three-dimensional diagnostics to do the experiment. You need three-dimensional DNS. So it's a tough problem, but a very important problem. I gave you some formulas last time, earlier, that said that the height of the liftoff region depends on is proportional to the velocity of the fuel coming at it, and it would be inversely proportional to the laminar burning velocity squared. So, you raise this velocity, lift it off, you put some hydrogen in here, and it'll go to a lower, more stable location upstream. So we understand the global properties of this problem, but we only beginning to look at the physics. Now, if you make it even more complicated, I talked to you about a gas turbine lean premix pre-vaporized device, and they would have a lot of little holes in which fuel is injected out, and then there'd be cross flow, which could be fairly substantial, and it would cause these jets in a cross flow that have very good mixing. And Andreas Gruber, who's from Europe, from I believe Norway, Jackie Chen, she's at Sendia, and they've published this work in ProC. And then another example is this is the DLR burner that Wolfgang Meyer and his group developed, and we ran it, and a student named David Rosenberg ran it, and we looked at the degree of partial premixing in that burner. I'll tell you about. So, lean premixed is the way of the future, whether it be with a liquid fuel and you vaporize it in some way and then mix it. But you want to mix the air in as quickly as possible to get low NOx, low CO, low soot. And there are a number of designs used by the jet engine people to get lean premixed conditions. And then if you're using natural gas on the ground to make electricity, you definitely can do lean premix, because if it growls a little bit, well, it's kind of noisy, but not too bad. But if you're flying around and it's growling, that's not good. So you have to get rid of the growl instabilities, especially in aircraft applications. And you need to study everything with high-speed diagnostics because everything is oscillating in time. And to model it, you need things like frequencies and phase angles. Now, I'm sure that Professor Kandel is telling you all about this in another lecture. What I want to talk about right now is flame index measurements. What measurements you might want to make to get going in this field. Autoignition. Now, if you preheat air and premix it with the fuel, there's a chance that it won't be burning, and then all of a sudden it'll burn. So, you know, in any of these premix type devices, a big problem is when you first start it off, you inject this premixed mixture into a chamber, and you light it off, and it's like your barbecue at home, you know, when you barbecue. You really don't want to leave the fuel on for a long time and then bring the match over, right? You've probably done that. You've created a premixed combustible mixture and you light it, not good. It's better to have the ignition source always on and then slowly bring in just the fuel, and whatever air is around will light and get this lazy yellowish diffusion flame, and then you add in the air and it's blue and intense. This is also a problem with rockets. You know, one of the big problems with igniting a rocket is that you have to be forcing hydrogen and oxygen into a chamber, and it has a little tiny throat in it, so it's almost a closed chamber. It's hard for the gas to get out. And then you ignite it, and so rockets can explode quite easily if you don't have a good flow going through and if you don't ignite them in a sort of a gentle way. Sudden flashback, that's a problem. If you put hydrogen in CO, and if for any reason you put a little more hydrogen than you wanted to, there's a good chance that the flame will flash back, or it'll anchor too close to the wall. It'll get close to the wall and cause too much heat transfer. If you have hydrogen, as you do with the syngas, the Lewis number can have a big effect, and it's hard to model. So the next step is just to ask, well, how would we model something that's partially premixed, sometimes premixed, sometimes non-premixed? The 5 models that I put up here are pretty much the same that people are using for premixed combustion. But because you see, it's harder to measure, it's harder to model the premixed, it's fairly straightforward and relatively easier to model the non-premixed. Because non-premixed is a mixing problem. The chemistry is pretty fast once the fuel and the air come in contact. But premixed is a wave phenomena where everything's premixed, and you want to make sure that the wave is propagating at the proper wave speed, which is the turbulent burning velocity. So you have additional criteria other than just, well, you don't have to worry about mixing, but you do have to worry about propagation. Flame surface density approach, filtered tabulated chemistry LES, pushed by the British at Cambridge and the French. And I see a Swedish person there, and actually a German person, so it's definitely a European effort. This is more the Stanford and German combined effort to use, again, a flamelet progress variable. This would be to, well, I'll tell you about how you would add, how you do it for partially premixed combustion. And then I mentioned this thickened flamelet model on the first day, and I'm not going to say much about it, but just remember you can make the model, you can make the flamelet as thick as you want if you artificially slow down the chemistry, put really low Arrhenius factors that are not realistic. The chemistry gets really slow, and you can also thicken the flame by making the diffusivity of heat unrealistically large. And Poinsot argues that if you do this in the right way, the two counteract each other and give you the right burning velocity, but then they work together to give you even thicker flamelets, and so you don't have to resolve anything thin anymore. But the question is that a real flame or not? And then these other models are very useful in that they can handle partially premixed combustion, but they're not completely developed. So if you're interested in reading more about partially premixed combustion, it's hard to find exactly what you want to read first because there isn't like a section partially premixed combustion in the literature. So you have to do a little digging. I would go with this modeling effort. Knudsen and Pitch talk about how to do it. Here is the M and C did a partially premixed gas turbine device and attempted to model it. Poinsot has a number of papers with a thickened flamelet model that are for partially premixed. Professor Menon has done 5 or 6 good papers on partially premixed, and this is one especially good one. Nayan Patel is at GE in Cincinnati, and I've interacted with him. He's a very, very bright young person. Please don't tell him I said that GE uses bad computer codes, which I said the other day, because he's one of the people who knows how to write really good modern LES codes, but as far as I know, they don't let him design engines yet with that. It's a little bit early. Some French and Germans work together on DNS. So you may have heard about this flame index. It indicates the fraction of flamelets that are premixed. So if you were to look at a non-premixed flamelet, a segment of a turbulent, wrinkled, continuous flame, you would see that there'd be oxygen on one side of the flame and fuel on the other side. And by Fick's law of diffusion, the O2 is diffusing inward and the fuel is diffusing inward. And where they meet is where they react. Whereas, as we know, in a premixed flame, or premixed flamelet, the fuel and the O2 are mixed, and so they both diffuse down the gradient to the right here, and then at some point they react when they get hot enough. So Takeno defined this quantity. Now, del YF is the gradient of the fuel, and so this vector will the gradient vector will point to where dyf dx is going, and so if yf is going up in the x direction, this will be positive, and so in this case, dyf dx is negative, if this is what we call x, and so the gradient is negative, but the gradient of O2 here is negative, and so they're both negative. And now, we just want one number for this segment of the flame. We don't care about the gradient here, the gradient here, the gradient here. So we'll take the maximum value. So we'll look at this gradient, and like right in the middle here, there's a maximum slope, and we measure that number, and we multiply it by the slope here that's maximum, not up here, not down here, but right here, and we take the dot product. In this case, they're both negative vectors, and so the dot product is positive. And then we divide by the magnitude of whatever that vector is. So this number can either be +1 or -1, but it can't be anything else because we're automatically normalizing by its magnitude. So in this case, this flame index is +1 because we have a minus number, and we get a plus number. In this case, we're going to have a minus number and then a plus number. And so this will be a negative number on the top, and the The bottom is the absolute value, and so it has to be positive. So this will become -1. Not too complicated if we could just figure this out in a turbulent flame. Now, why would we want to use this flame index? All the models that attempt to do partially premixed combustion involve a Z equation and a C equation. Z is the conserved scalar, the mixture fraction. You can think of it as proportional or depends on the local fuel-air ratio, but it's the mass fraction of H atoms properly normalized. C is defined by different people in different ways, but we might as well just think of it as a non-dimensional temperature. And so this is like the energy equation, and then this is the reaction rate term. And as we said before, we can close this problem if we could just make two assumptions. First, we assume we have flamelets. So we get the reaction rate as a function of the independent variables Z and C through some Chemkin mechanism for laminar flames. And then we have a PDF that's a function of Z and C. We integrate these two and we get the mean reaction rate. But the problem we have now is that sometimes we have non-premixed, sometimes we have premixed. So Knudsen and Pitch suggest an approach, and Domingo, Bray, and the French group, they suggest basically a similar approach, but with different modeling equations, but it's pretty much the same thing. The PDF of this flame index is bimodal. It can only take on two values, 0 or 1. Xi can only be 0 or 1. So you think of it two delta functions, one at xi equals 0 and one at xi equals 1. So when you integrate, see, did I? Just want to check one thing here. Okay, I didn't change that. Thought I did, but I didn't. This is the fraction of flamelets that are non-premixed. Now, what it really should be is the integral of P d xi around xi equals 0, because the PDF is actually a delta function, and the area under the delta function is a number. And I think I did it right in a later slide. So, you know, when you take the integral of these two things, which I showed in the last slide, it really should be the integral of P d xi. So this is sort of like the area under the delta function at xi equals 0, which means non-premixed. But then you want to multiply by something that tells you the average reaction rate when the flamelets are non-premixed. And we're doing this all within a computational cell. In other words, we just get this number out from this calculation, and then we assign it to one of the corners of the computational cell and do the rest of the LES simulation on the grid. So we don't really know what's happening inside the cell. We're just going to say that whatever is happening is going to follow this equation. And the fraction of flamelets that are premixed would be this, and we'd have to come up with this. So it's sort of like a switch. It says, let's say 50% of the flamelets are non-premixed, so then you would run your non-premixed flamelet calculation, where you would take the mean and the variance of the PDF and put in a non-premixed flamelet state relation and compute this number. And then you should then repeat the whole process now for the premixed state relation. So you're running Chemkin to get a whole lot of non-premixed flamelet solutions, and then you run Chemkin again and get a whole lot of premixed flamelet solutions. And if you fold them in properly, you get hopefully the right answer. Okay, That's the idea of the two major models that I'm going to reference and talk about. And then once you do that, you say, how do we assess something like this? We have to find an experiment that's partially premixed. Well, I showed you that there are three examples of the lifted jet, the jet in a crossflow, and this is also a lifted, initially non-premixed flame that is in the DLR burner. You put fuel in here, you have swirling air coming around, and both on the outside and the inside. And you end up with a fairly flat-looking flame, and it's mixing a lot in here, but not completely, so it's not a premixed flame. Some of the fuel in the air haven't fully mixed, but then a lot of the fuel in the air have premixed, and so the work at DLR, they made a lot of measurements, but they didn't measure the flame index. And so they have the velocity field, temperature, lots of other variables. And this is what the flame looks like running in our lab. David Rosenberg ran it, and it looks pretty flat. It sort of has a hole in the middle, but you don't see that from here. But you can see that there should be some flamelets here, there should be mixing here, and nobody had really looked at the flame index before. So I asked David, actually this was on a previous NSF grant, which we're very happy to have had. David did a great job. He's finished his PhD and published papers. He's got a job, which is number one, right? And he actually got a job in the city he wanted to work in, which is Washington, D.C. He did his postdoc at NRL, which is in Washington, and then both he and his wife wanted to stay there, and so he got a research job that's partially research and partially, governmental related in Washington. He's really happy doing that. But what I asked him to do is I said, well, David, can you find some way to measure this flame index? And the first thing he did was he looked at all the diagnostics that Ron Hansen, the Stanford people, and all around the world, Marcus Aldin in Sweden, everything. And finally, we realized that we'd have to add a tracer to the gas because there's no way you can you can't measure these mass fractions. We need images to get the gradients. We'd like to have three-dimensional images to get the three-dimensional gradient, but we can only do it in a sheet. So you need images, so you need fluorescence. What fluoresces? Well, it's not, you can't really find a fuel that fluoresces by itself unless you run pure acetone, and we didn't want to do that. That was really sooty and nasty. And so we decided we'd add a little bit of acetone to propane. And the reason is that both acetone and propane are pretty heavy molecules. They both have diffusivities, molecular diffusivities that are fairly large. And if you look them up, they aren't that much different. You wouldn't want to add acetone to hydrogen, for example, because it wouldn't follow the hydrogen very well. If the hydrogen wants to diffuse this way, this acetone's a really big molecule. It wouldn't follow it. And so adding acetone to propane, and then we ran Chemkin. David ran Chemkin. And this is what you get for, this is for a non-premixed flame. The fuel in the acetone disappeared, not exactly at the same rate. Actually, David, this was several years ago, he wanted to find out a mechanism for acetone. So he said, hey, there's somebody over in Ireland who has this kind of chemistry. And I said, oh, yeah, Henry. So he emailed Henry's and one of his students. And so Henry was very nice a long time ago to provide us with the chemistry mechanism for acetone that we put into Chemkin and allowed David to do his thesis. Okay, so I thanked Henry the other night again. But that's what the beauty of Chemkin. It can just tell you this information. And now we said, well, what can we add to the oxygen? Because O2 doesn't fluoresce. We thought NO because NO is also an oxidizer, but the trouble with NO is that it's created in the flame. So if you run ChemKin, what you find is you get the NO profile isn't this nice smooth blue line. It's gonna be kind of a wiggly line that goes up and down and kind of ugly, and you don't know if the NO that you measure is the NO that you put in with the air, or it's something created in the flame. But the flame doesn't create any NO2. The ChemKin verified this. So you can see the NO2 goes up and the O2 goes up. Now, it'd be nice if these two curves overlapped, because then we could say we can measure the actual concentration by measuring the concentration of the tracer. But they don't overlap, and we don't really care, because we're not trying to measure the concentration or the mass fraction. We only want the maximum gradient, and we only want its sign. So the gradient of fuel is negative here, and the maximum gradient is right here, and the gradient of acetone is right here, and it's negative. The gradient of NO, right, the maximum value is right here, and it's positive. And here, this is positive. Now, the one mistake we're making is that the location where we say the gradient is slightly disturbed from where we measure it. But David has a way of accounting for that. In the premixed flame, it's the same situation. The O2 drops as you go into the flame, and the NO2 drops, but they don't drop at exactly the same place, but their gradients are both negative. And even then, we don't care about the magnitude because we divide by the magnitude here. So all we want to be sure is that this quantity has a negative slope wherever this quantity has a negative slope. And it does, except for that there's a little now this is about 1/10 of a millimeter, a little more than 1/10 of a millimeter. So it's not a huge problem because we can measure much more accurately than 1/10 of a millimeter anyway. This is kind of like our spatial resolution. So this looked like a promising idea. As it turns out, we were down in the lab and we couldn't get enough signal out of all this. The NO2 didn't have enough signal, and this is what I told you earlier. We realized we needed a better camera that was red sensitive, and so it looked so promising we decided we'd just buy a new camera, and we did. And David went from no thesis to thesis in a couple of weeks. Actually, we borrowed the camera. You may have this experience. We borrowed a camera from the company that sells them, and he said, "Yeah, you can try for a week," and we did it, and like eureka! And David goes, "Hey, I'm going to get out of here." You know, and so we bought the camera, and it worked. But now here's what you get if you put NO2 in the gas in a highly turbulent situation with a flame present. You get the NO2 is all over the place, and we're arguing that it's tracking the O2 fairly well. And if we put acetone in the fuel, you get pictures like this in here, and we're arguing that it's, to the best of our ability, tracking the fuel. Then we take the derivatives, we take the gradients in space, so the derivatives in two directions. And that's, once you have the data, digitally recorded, you can just use MATLAB. You have to remove any background noise, and we did this in laminar flames first to make sure we knew what we were doing, and we got good results in the laminar flames because we know which direction the gradients are, and we would have a perfectly premixed laminar experiment. We'd have a perfectly non-premixed laminar experiment, and as you might expect, we could easily see that it was giving gradients in the right direction. And he also found that he could get enough signal to noise with a lot of work, about a year's worth of work just to get the pictures on the last slide looking like the pictures on this slide. Now, each pixel here is handled independently, so it gave us a real good feeling when we saw that we had a very continuous-looking flamelets. Now, they're not completely continuous, and they're not really extinguished, we don't believe, at any of these points. It's just that the signal-to-noise is not good enough in some spots. Okay, but we're not trying to, we're going to be taking averages of all this anyway. So we're going to average all the red regions and all the blue regions, but the blue regions would be surrounding globs of fuel, where air might be coming in on this side and fuel coming in on the other side, whereas these red regions would be surrounding premixed reactants that we don't know which, well, I can't tell from this picture, but from his data, he can see which way the reactants are coming in. So I'm going to guess that they're coming in upward. Okay, so no one had tried this before, and it seemed to be working pretty well. He had to remove noise from the images and apply an edge detection algorithm just to make sure that we are looking for gradients about in the right direction. And then he has to conduct a search to match each acetone gradient with its nearest NO2 gradient layer. Because we want to find out is if you have an acetone gradient, is the NO2 gradient nearby in the same direction or in opposite direction? So he started from the left, proceeded to the right of the image, and then his computer code would then identify a pixel that's in an acetone layer and determine the direction of the gradient. And then he proceeds along he determines the normal to the gradient, and then he proceeds along that vector until the next layer is detected. And if there's no layer nearby, then there's no flamelet there. It could be just be a gradient of acetone, and there's no burning at that point. But we're arguing that if it's a premixed flamelet, he'll find an NO2 layer very close by that has the same direction of the gradient as the fuel. And if it's a non-premixed, he'll find another layer nearby that's it has the opposite direction of the gradient. Now, the only thing we're trying to get is to assign to every pixel on that flow field either a red or a blue color. Okay, so let me go back here. Everywhere in this whole flow field, he has data. And you see, we just want to put either a red pixel or a blue pixel at each point, or no color if there's no flamelet. Now, as we did this, we realized that there are lots of other things to check just to make sure we're doing this right. You can imagine if you have a reacting non-premixed flame, I said you would have fuel coming down here and oxygen coming up here. Now, in a real non-premixed flame, you really don't have much overlap of the gradients, okay, because there's almost nothing there. They're burning. So in this, you can see the gradient here is this way and the gradient here is this way. What you need to do is to match these two up, and then just take the maximum gradient of this profile, multiply by the maximum gradient of this profile, even though they're not at the same location. If you can argue that that's, within the distance of a laminar non-premixed flame, then you're okay. So you can't use this Turbulent index and get the two gradients exactly at the same location in a non-premixed flame. In the premixed flame, you can, because the two gradients lie right on top of each other. But also in a non-premixed flame, there's going to be a distance between these gradients. It's what we saw in the laminar flames and in Chemkin. There's very little, because the acetone or the fuel disappear, and then where does it react? Well, it's actually that you form hydrogen, H2, you form carbon monoxide, you form all the intermediate species, and then even the oxygen breaks down into O and OH and all that. So in a diffusion flame, you generally don't have a whole lot of O2 sitting right on top of the entire fuel. You know, everything is broken down by the time they react. So if a typical flamelet has a gap between the fuel and the O2. But if it's non-reacting, the two overlap because there's no reason for them not to coexist. It's just some fuel mixing with O2. So that's another check that we perform just to make sure we're doing this right. Could there be regions where the fuel and the O2 are looking like this, but they're not burning, like an extinguished region? And so what he did was he looked at these gradients and he threw out about 5% of the data, which would have indicated that there's a non-premixed flame, except that there wasn't a gap here. And so we said it couldn't be a flame, it must be non-reacting. Okay. So he did that, and this is the kind of information we get. Now, he also did an uncertainty analysis. You're probably thinking, you know, there's lots of uncertainty and inaccuracy whenever you do something the first time. And he did an uncertainty analysis, and you know, this allows us to get numbers that are reasonably interesting, but with some uncertainty. So again, I said the fact that he's getting these individual pixels to be right near each other means that we're doing something right. Because if we were doing it wrong, we just kind of get random blue and red pixels everywhere. But we're resolving structure of continuous layers most places, and you can see what you get. And we tried different equivalence ratios, different fuel injection velocities, and got a data set. But then, you know, what would the modelers want? If, you know, I visited Professor Bray in Cambridge, and I told them we were doing this, and they said, what do you want? And he said, well, we don't want any of those pictures. They have no use to us. What they want are these kinds of statistical averages. So in this particular case, we're looking at the fraction of flamelets that are premixed. So what you do is you first identify whether you have red or blue flamelets, and then you count up how many you have. Like in this region right here, you look at thousands of images, say 2,000 images, and you say, well, if I have a flamelet there, is it a red or a blue flamelet? Okay? It's just a conditional average. It's not the average flame index at that point, because the average flame index is like a really small number, because most of the time there's no flamelet. But this is a conditional average that if a flamelet is there, is it red? And if it is, then you get these big red regions. And if a flamelet is there, is it blue, which would be non-premixed? And this is what you get. So now the two numbers should add up to 1. You know, if it's not red, it's blue. So, but this is just the probability of the flamelets that are premixed, and so the fraction of flamelets that are non-premixed would be 1 minus this number. But you see here, I don't know if you can read that, but this is like 80% of the flamelets are premixed, and down here it's more like 20% are premixed. So, in here it's 80% are non-premixed, so this is mostly non-premixed. Now we can only look above the burner. This is the center line right here. There's an annular fuel injector, and so the fuel comes up and goes like this, and so it isn't too surprising that where we can first see flamelets above the fuel tube, they're non-premixed, and then as they mix in with a lot of air, and the fuel and air mix, you get more premixed. Okay, let me go on here. These are more, this is the same run, except at different times you get different pictures here. Sometimes lots of red premixed flamelets, other times lots of blue. And then we said, well, is there anything to compare this to in the literature? And no. But there are a few LES simulations that are at much lower Reynolds number, but they attempt to, they have attempted to compute the flame index. Now, Heinz Pitch, and this is after we did all of this, we looked in, here's a paper by Heinz Pitch, and like, Heinz has computed everything, right? I mean, if you're ever looking for something that's been computed, and you say, gee, I wish somebody had computed that, just Google his name, and he probably has done it, right? So we were overjoyed when we found that he had done DNS on a burner that was very similar to ours in geometry, but the flow velocities were much lower because he was limited with DNS to low Reynolds numbers. But you know, it's the same sort of thing, an annular fuel injection through an annular thin region here, and then air coming up here and air coming up here. I guess it's not too surprising since he's in Germany and we got the burner from Germany. It's kind of the canonical design. Okay, so he showed that in his DNS they get red premixed regions here. Green was non-premixed, and so you know, it's very hard to compare this to this, but they look like they're outside. And then the black is where the fuel is, the center of the pure fuel, which he put in his ProC paper. So when we finally published this, we got criticism from the reviewers. Why don't you get a DNS that's a lot more realistic of your experiment? And my approach is, we're lucky we got this one, you know, because it was an incredible feat to simulate this with DNS and to compute the flame index. So he basically has given us the flame index, and all we're arguing here is that these pictures are not inconsistent with these types of pictures. And then, of course, we looked further and we found that Professor Menon at Georgia Tech had done a DNS of a swirling flame. It's a little different geometry and everything, but he put the premixed region in black and the non-premixed in white. But both of these people realized the importance of getting this flame index. And you know, our results are also, I guess, not in contradiction with this DNS. What we're arguing is that most likely there's a core to this fuel jet. There's a shear layer. It's flammable somewhere in the shear layer, but it's not burning because the velocities are too high. And so it's a lifted flame. And then most likely there are triple flames, but I'm just guessing here because we have we couldn't find any strong evidence of triple flames. You know, for one thing, we're only in one plane, and it may be a triple flame at some other place. But if there were triple flames, you would expect a lean branch over on the lean side and a rich branch on the rich side, and then a diffusion flame coming out the middle. And then you would expect that if this was all shredded apart, then there might be fuel and air pockets, and there might be premixed flames burning around some or all of those pockets. And that's sort of what we see. We see a bunch of non-premixed flamelets in here, and we see a lot of premixed flamelets out here. And of course, there's swirl in here, so there's recirculation. So there's a good chance that a lot of air will get into the problem up here. Okay, so it'd be nice to do this, now that we sort of know how to do it, it'd be nice to have other groups do it and maybe make similar measurements or do DNS that are more related. But this is where we are. So I'll repeat some things here that partially premixed is the way of the future because of the low pollutants, because of the use of natural gas as well as syn gas. And most devices have a lifted flame because they don't want the flame base sitting right up on the injector plate because that's too much heat transfer. And so if you talk to GE, they'll say, oh, we have a good flame, and they never talk about lifted or blown out or anything. They just say it's a good flame, it's sitting about where they want it. And to me, it's a lifted jet flame. It's partially premixed. Okay, we need better models, we need better measurements, but what we've done with laser diagnostics is show that you can analyze this. Now, if you had Raman measurements, you could do better than what we did, but you'd have to get a sheet because we want to take gradients, and a single point won't give you gradients. So if you had a Raman sheet method, you could do better than us. You could get the actual fuel and O2 to give you a signal. I know at Yale, Marshall Long did some Raman sheet measurements some years ago, and I think the upshot was that, based on what lasers that were available at that time, the signal to noise was not real great. He actually put the laser sheet in a resonating cavity. So he put two mirrors on both sides. So you take a laser sheet, hit it into a curved mirror, and it comes back on top of itself. And so it's like a laser. A laser works this way with two mirrors. And so you get the sheet to bounce on top of itself like 15, 20 times. And so like you get 20 laser sheets all in the same plane. But that's really difficult to align, to get to work right, and so I haven't seen any papers since the Yale work on laser Raman sheet imaging. But that would be better, and maybe there's a better way to get fluorescence from some of the fuel or the oxygen. Now, I haven't seen any papers on getting O2 to fluoresce or any fuel except for some nasty fuels to fluoresce. So there are ways to get better measurements, and probably better DNS is what would help us the most right now. And then all of this is important because growl instabilities occur, and there just isn't any good model that the industry has to tell them two things. What is this growl and what's it doing? But secondly, when does it start? So a really big question is the incipient growl. That is, at what fuel-air ratio do we get these acoustic instabilities that Professor Kandel talks about? So that's another big issue that I think some of you may want to look at. What happens with these instabilities? I think I'll stop there because we'll take a little break and then I'll talk about models. And if you're expecting me to give you the answer, don't, because the models are pretty primitive, but we'll talk about them anyway, okay?